Hi guys, welcome to our channel Science Beyond Books, and we are back with fourth episode of Science and Research Simplified. We are very happy that we have one of the young scientists from Europe, and he's going to talk about solar energy harvesting, which is very important question because it's associated with the saving our planet because there is a lot of global warming happening. We are not taking care of our planet, so it's very important to use the energy in very wise way, and that's where solar energy comes. So he's going to talk about how we can harvest solar energy and how we can, what kind of research is being conducted in that field. So let's welcome Sudhanshu. He's going to talk about uh, solar energy harvesting. Hey, welcome. How are you?
I'm pretty good, and thanks for having me on your show.
Yeah,
And
it's pleasure. Yeah,
congratulations on this very good initiative of
yeah,
this.
thank you so much. I'm very happy that you got time for us, and we are doing this show, and it will be very helpful session for youngster like school going student, college going student, because they will come to know not only just about the research but also about why it's important to talk about solar energy or green energy, and how we can save energy, how we should not be wasting energy, because what is the cost of wasting energy. So it's going to be very important topic, and I'm very happy that you are going to talk about it. So, guys, before we start today's talk, let's introduce today's speaker. He's Dr. Sudhanshu Shukla, and about his background, he did his undergrad and masters from BHU, which is Banaras Hindu University, and then he did his research in IIT Bombay. And after doing his research in IIT Bombay, and that's where I think he got interested in research, and he wanted to become a scientist after that. And after conducting his research in IIT Bombay, he decided to do his PhD from Singapore. So he did his PhD from NTU, which is Nanyang Technological University, and that's how I know him, because we used to work together in NTU. And he has a collaboration work during his PhD from University of Berkeley. So his PhD was joint PhD from NTU and University of Berkeley. And after finishing his outstanding PhD from NTU, he moved to University of Luxembourg, which is a small city in Europe, in a small country, sorry, in Europe. And that's the mistake people do, that it's city. I'm the same. It's a small place, right?
Indeed, yeah, very
Yeah,
small, very beautiful, very powerful. In fact, it's at the center of the Europe. People find it really hard to locate it. Even the immigration officers, to
that's
my.
that's that's true. So that's where he did his. He's doing his postdoctoral research, and he's conducting his research in solar energy harvesting. So that's what he's going to talk about. I'm very happy to have you here, Sudhanshu.
Thank you very much. And with this, I will share my screen with you.
Yeah. So
So
if we start, today's talk, for the people who was watching the previous stream, there was some glitch, so we started a new stream. So if you are there, you come and join this stream. Yep. So if you wanna bring your PPT,
yes, and that's in for Hindi audience. We call it technological dushwariyan. This.
absolutely, and it
So
happens every time.
I'm going to show some grim scenarios that you see around you, but you probably choose to ignore you or maybe just post it on your
But
wall
you
and
have
pretend.
you have not shared your screen,
Yeah,
Sudhanshu.
yeah. I'm just talking right now.
Yep,
So
yep.
building the momentum. Um, I think now you should see the slides on the full screen, right?
And slide looks awesome because at least we can see it.
Yes.
Yes.
So
Go ahead.
I hope you all can see the slides now. What
Yep.
I'm going to talk about today before stepping into this very vital problem of solar energy harvesting sounds pretty cool idea. But we really need to understand why are we doing all this? Why do we have to save the planet? Are we really in danger? Why there is a need to save the planet? So I'm going to show you the grim scenario that we probably choose to ignore and post it on our wall and pretend to be social scientists rather than really doing onto something. And we can all play our part, but let me start with a little bit of background because this show is all about discussing research and science. Why do we do research anyways? I mean, this I excuse for having a digression from the subject here because this is not related to global climate change, etc., but just the very nature of research. Why do we do research is because we have problems and we have to solve them. So we do research. Yes, as a humankind we have to progress, so we need knowledge to do that. We generate knowledge for survival. I mean, nowadays I hate to mention it here, coronavirus. I mean, you all You all are here not to mention about hear about coronavirus, but for survival we need research. But there is a last bit of category which I call it curiosity. And if you look at this slide, you have two paintings. One is Van Gogh's painting, a depiction of the night, and one is the Mona Lisa's painting. Now, one would say, is there anything to do research about this? I mean, that's up to my curiosity. I want to know the philosophy behind it. But who's going to fund this? But yes, this is a problem for a research one might be interested in, but you need to find someone who would be willing to fund you for this. So in essence, this is not a worthless research. This is also a research that will be useful to mankind, the curiosity driven research. So this was, I was just wanted to put all this into perspective, that
Yeah.
one research is important, why not the other one is important. But this is also something really important. That's why we call PhDs Doctor of Philosophies. We are not building up the spaceships the way we imagine the scientists. We all do philosophy, we do thinking, and so that we generate knowledge that can be useful for the mankind. So with this, I move on to the real subject. You all know that energy is probably one solution that is one solution that actually can address to many problems. When we woke up in the morning till the time we go to sleep, we consume energy. We wake up, we ask our electronic assistant, I'm not going to name it, otherwise she will be active, Alexa. Uh, from there, we step into, we start our mobile phones, we use electronic gadgets, everything we consume, we consume energy, and that uptake is actually increasing. If you notice yourself 10 years before from now, you would find that you are actually consuming more energy by yourself. So energy per capita consumption is increasing every single day. Now, with this comes a lot of problems. We have a problem of economic development. For that, you need energy. You have an ever increasing population. Right now, it is 7.8 billion, and we are still increasing. We have climate change. We have diseases, by the way. And one would think, why would energy scarcity would lead to diseases, right? It's how do we link it? But just hold on. We have wars happening because of the natural resources, which are the key energy resources for us. There are wars going around, right? So if we have a source of energy which is free or widely available, at least without any partiality, which is everywhere, that would be a win-win scenario for the whole world. Well, I said, how can you link it to diseases? Well, yes, when you have climate change, you have global warming, you have temperatures going up, you have different kind of diseases, the occurrence of the diseases goes up. So therefore, all these problems are actually linked. So the point, the takeaway that I want to give you from this slide is that one energy problem, one solution, harvesting the energy, could solve all these problems simultaneously. So if you look at in the big picture.
Okay, so that's where I want to ask you one question that so why this problem of energy is so big? And also you mentioned in your title that our Earth or our planet is in danger. So what do you mean by that?
Yeah.
If you want to explain that.
So if you go to the background that I said we are consuming energy. Now we must think where this energy is coming from. That energy is coming from burning the fossil fuels. All the energy that we consume today predominantly comes from the fossil fuels. And when you burn fossil fuels, you emit more carbon dioxide in the atmosphere. That's not a big problem because that we know it, that it happens. But we are running out of trees as well. We are cutting trees, and then the trees which absorbs the carbon dioxide, they are not there anymore. So all that carbon dioxide goes into the atmosphere. It is filling up the atmosphere with tons of CO2 gases. Now what happens? We are not running out of fossil fuels. We have plenty. We are running out of atmosphere. We do not have enough space in the atmosphere where we can put all the CO2 emissions.
Yes. Yeah,
Have.
true.
So, to cope up with this demand, to cope up with the economy, to cope up with the population, to cope up poverty problems, yes, we have a choice. We can stick to fossil fuels and ignore the problem, or we should think of something which is cleaner.
Okay.
But we have to save the planet because we are running out of atmosphere. With this, if you look at the same thing I'm showing you in terms of this data representation, what you are looking at over the years, the energy consumption has increased. So as the we have different sources of energy. For example, oil, coal, gas. Predominantly, that's what we have been using, and that's why you see the curve has been just skyrocketing. Um, You see, the curve is just going up exponentially. And today, as of now, we are consuming around 15 to 18 terawatts of energy. And if you project it within next 20 years, this is only going to be doubled, because we are not going to stay the way we are. We will evolve. So we will consume more energy. We will consume more oil. We will consume more natural gases. But if you, the good news is that the renewable energy sources, which are clean energy sources, which do not emit CO2, the share of them is actually increasing. If you look at this green bar, it's slowly picking up. We are slowly learning to go more towards renewable energy. We are harvesting wind more, we are harvesting solar more than ever before, and the capacity is only increasing. That's a good news. But the bad news is that we are probably at the point of no return. Even if we stop it, like we decide not to use fossil fuels from tomorrow, maybe we are a little late. But it is never late. No action we take, the humankind takes, is late. But we are at a juncture that we have to do something. And still, even after seeing that we are consuming so much of energy, up to your surprise, we still have 13% of global population which is living without electricity, which is nearly 940 million people. So we still have to go a long way from here. We are not done. And with this, as I said, why CO2 is so important? Even if it is going in the air, it's fine, it's okay. But no, if you have more CO2 in the atmosphere, the sun rays that comes in every single time, okay, not in the night, it gets absorbed by the CO2. And when it absorbs that excess sunlight, which was not there before, the atmosphere heats up, and slowly, as the CO2 parts per million we are talking, the concentration of CO2 we are talking is of the order of parts per million. So if you look at the bottom graph, you see there are fluctuations in the CO2 emission. This is in parts per million. It has always remained below 300 parts per million, which is shown by this dashed line. Only now, within the past 50 or 100 years, after these post-industrialization era, where we have gone through rapid economic development, we have unprecedented level of CO2 level present, which no humankind has ever seen in the history.
Oh,
So we're at the maximum level right now. And with this, the temperature is also picking up, because now you have more CO2, the temperature is rising. Right now, and you know what, up to your surprise, if you look at the graph, it shows fluctuations, it shows dips and ups. The dip is where your CO2 levels goes down. And these dips are actually responsible, but there is no scientific proof of it. But what scientists believe are the reason of ice ages that have happened over the past thousands of years. We have gone through the cycles of ice ages. So these fluctuations are responsible for that. Now you can see what the damage this CO2 level could do in future. And right now we are standing at a level where we have 1 degree Celsius rise in the global temperatures. 1 degree.
so can I ask you one question here, Sudhanshu? So as you mentioned that there is, so we can understand that CO2 level is increased to tremendous level and it's very dangerous. But overall, you mentioned that it just increased temperature, global temperature by 1 degree. Is it that dangerous to have just 1 degree temperature rise? How it gonna impact our life? Like, is it
That's
just 1 degree or it has a bigger impact than it seems?
Well, that's a very valid question. And when the policymakers or the leaders ask, "Hey, 1 degree hardly matters. I go in and out of my office, and the temperature changes by 15 degrees, and that's okay. Degrees, who cares?" But let me show you. This is the average temperature, and this is slide. I will show you. If I'll play this nice little movie, on the x-axis, what you see as the time progresses. So this is a distribution of the temperature. The low tail is actually, okay, let me go to the lower tail represents the lower temperatures, and then you have this wing of higher temperatures, and somewhere you have the average. So how scientists would have measured this is basically measured the temperature all across the globe, and then they plotted it, and what you get is the nice bell curve.
So this is basically highest and lowest temperature.
Yes, and
That's
this
the range, and you are usually in the bell safe in the middle of temperature. That's
yes,
the average temperature. Yeah,
the middle is actually your average temperature.
yeah. Okay, makes sense. Yeah,
Yes. But what we are missing here is that the temperatures which are at the extreme, if you look at the high energy tails, that are extreme temperatures because, and these are responsible for the heat waves. Like at some part of the world, you have heat waves where you have famine, drought, or maybe cyclones. So what you are noticing is that the frequency of such events have only gone up, and that's not because the average temperature has risen. It's because when your average temperature rises up, this bell curve, if you notice, the bell curve will slowly move to the right. And so as the tail, you see the tail is now expanding all the way to the higher temperatures. So meaning you have more areas in this whole planet which are at extreme temperatures.
True.
And those extreme temperatures, you can have warming of the ocean, you can have droughts, you can have famines, you can all sorts of events that you are familiar of now. And you see that the frequency is increasing day by day. That's why it's critical. And 1 degree is doing so much of damage. Now imagine with the level of CO2 we are emitting today, and if we keep going on with the same pace within the 30 years, the temperature rise won't be 1 degrees, it will be close to 3 degrees, 4 degrees even. What that can do, it can do a damage which we cannot imagine. First of all, if you look at the ice melting, and this is what you are looking at the North Poles, somewhere 50 years ago, nicely covered with the snow, and now at the bottom, you are looking at the scenario 2017 or 2018. A lot of ice has actually melted. Is that a problem? Nobody lives there. Why should I care? No. There are two problems. One problem is that when the ice melts, you have permafrost. Permafrosts are basically tiny little packets where the CO2 lives in. And if they melt, that CO2 goes all the way off in the air. And that accelerates the temperature, accelerates the warming because now you have more CO2. Now that accelerates further frost melting. So this, it kicks off a non-linear process. And then eventually you have more CO2, more warming, and this is a catastrophic effect. And same if you look at the sea level rise. Of course, when the ice would melt, the sea level is bound to rise. And if it rises by about 1 meters, which would happen if you have a 3 degrees Celsius rise, half of the Miami would be underwater. You should not care about Miami, maybe because you're not living there. Maybe Ajit, you are quite close to Miami. But those who are living in Mumbai, on the coastal areas, Singapore even, they should worry about this and they should brace for this. They should be thinking about this, that this should not happen. If you look at the CO2 levels, this is just 40 years back. You see, quite low, but on the lower graph, it is red all over. So the intensity has only gone up. The CO2 levels are higher than ever before, and so has the temperature. So the top graph actually shows you the temperature 40 years back. The bottom shows that now it's red. And especially if you notice, the poles are getting hotter. That's a really, really bad news for us. Because, okay, let's do this experiment. If you have a water bottle and try to put CO2 inside, what happens? I mean, we know soda, right?
Yep.
We make the water more acidic. So your oceans are getting more and more acidic. That is affecting life. That is destroying the corals. The whole marine life is also getting affected. You see, this problem is pretty much linked.
Yeah,
So
so
not just
that's a good point because I never thought in that direction that CO2 has obviously it's a gas and it has a different it harms us in a different way. But yes, that's a good valid point that it will make water more acidic and that will have a huge impact on aquatic life. So that's
yes.
very yeah.
For example, I mean, some of the creatures that live in the water, they have adapted to a certain pH, so they reproduce at certain pH. But if you increase the pH, reduce the pH, sorry, make it more acidic, then their reproduction suffers. Some of the species might even get extinct in just a matter of 4 or 5, in maybe 2 or 3 decades.
Yep,
You won't even find them. That's very alarming. Now,
that's
I have mentioned a word that is written at the bottom, climate epidemiology. This is a word you have been listening to this probably for the 5 6 months, and I hate to mention this again here because of the coronavirus. That the experts are analyzing the data and they call it epidemiological investigations. What
true.
that means is that you notice the number when you don't have the knowledge about the subject, you rely on the data and then you try to figure out what's happening based on the
That's the
data.
consequence. Yes.
What's the consequence? So let's say you're talking the number of infections goes up at day one, And the number of deaths, I'm sorry to mention it here, but just bear with me. The number of infections goes up today, and after 3 weeks, you see the number of deaths peaking up. So you see a lag of 2 to 3 weeks, which is roughly the incubation period of the virus. So it takes the damage to be visible to us to 2 to 3 weeks, because that's the incubation period of the virus. That's called epidemiological investigation. Now you apply the same thing here, you do climate epidemiology. That 3 weeks for the virus could be 40, 50, or maybe hundreds of years for the planet, the effect to show. So the temperature rise of 1 degree now would have a long lasting consequences, and maybe in a decade or so we would be able to see that.
So,
We
so
don't.
what you are trying to say that is, like the example you took for the epidemic going on is, so it's like the infection which happens, right? And the result we see after, like, a couple of weeks. Similarly, the damage we are making now, and
Yes.
what will be the consequence, what will be the outcome of that, will will come to know after like 40, 50 years later, and that's what we're going to give to our children, or our future
Precisely.
humans. So that's what we have to be careful about, like, because we might not be there after 60, 70 years, but there will be people around, and that's the world we are going to leave behind. So I think that's what you're trying to say, right?
Yes. The point I want to make is that don't wait until you see the damage, because the damage is already being done. It's just that you don't see it.
Yeah,
And
because we are not seeing the result, but damage is done for sure. Whatever damage
yes.
we did so far.
So you have a choice. I mean, you chose to become an ostrich, put your head in the sand, and pretend nothing is happening. Or if I die, who cares? I mean, as long as I'm alive, I'm living a luxurious life. It's okay. It's fine. But you have to think in this way. If you are comfortable with this experiment, human beings are not perennial.
Yep.
We are not primordial, and we won't be perennial anyways.
True.
So if you're okay with that fact, it's okay, completely okay. But that's the world we are going to pass to our children. That's the legacy we will give it to them.
Yes, that's a very valid point. Yep.
And this ostrich refers to us so as to the leaders who probably chose to ignore this problem.
So with that, I want to ask you that what are the other source of energy, like from where we can harvest energy? There should be different ways to harvest energy and save planet, right?
I was almost there. Like so
Yep.
far, I only showed you all the dark scenarios, like a movie that starts with a tragedy, and now the good part.
Yes,
So
yes, sure.
if you notice, we have a plenty of renewable energy sources. We don't have to strictly rely on the fossil fuels. Even if we become greedy, we know it's there. The problem is actually the extraction costs and all the technology, but that will eventually come up. The innovations are happening every day. But now let's look at the renewables. What we have? We have wind, intermittent. So you cannot predict the output from the wind. You have hydro energy. You have geothermal. And if you look at the sun, this big circle represents, that shows you the potential. The bigger the circle is, the sphere, or rather sphere, is, it shows the higher the potential. So if you look at the sphere from the solar, it's about 23,000 terawatts, which is 16 terawatts, way higher. But that involves an assumption that 1 hour of sunlight that falls on the Earth's surface is enough to power the whole planet for the entire year of energy consumption. That is huge. But then 1 hour of energy, the sunlight that falls on the Earth's surface falls everywhere. You have ocean, you have land, you cannot install sun. So that's an exaggerated statement. But the point here is that even if you're able to harness few percentage of it, that would be enough. So we have a source which is an unbiased source, which shines equally well in the poor countries and in the rich countries. There is no monopoly over it. We can harness it. We need to know how to do that. How can we use this solar energy to get electricity out of it, or to get fuels out of it? Do we know about solar cells? Do we know about them already? This is how this whole idea came into the picture. That actually came when you look at the plants, what they do. They consume the sunlight, the process we all know called photosynthesis. So they capture CO2, use the sunlight to convert it to make this very valuable hydrocarbon, which is a fuel, and then out goes oxygen. So this is a cycle. That's fine. So if you consume CO2, gives off the oxygen, that's a carbon cycle, we all know. But what if you emit CO2 more and then you cut the trees? So you have more and more CO2, but So the point here I want to make is that trees are already doing it, but they are not quite as efficient as what the scientists are doing in the lab. The process of this, the efficiency of this process is less than 1%, because plants do not have to worry about running a vehicle or car. They have to worry about their growth. And for their growth, less than 1%, precisely 0.3%, is sufficient. So they are doing it enough for what they should be doing. For us, we need more efficient cells, artificial photosynthesis, so called. Can we use this idea? Yes, we know about them. We have seen them in plenty of places. Let's look at this. You have all seen these solar panels somewhere. Okay, these blue color panels, these are made up of silicon. And when you have a scarcity of land, something like a country in Singapore, let's say, you have this is a megapolis full of skyscrapers building, there is no space. Where would you install them? A good idea would be to put them on top of the water, because that's a kind of a land which is available, I mean, a water body that's available. You can use that area for the
That's a brilliant idea. I mean, I did not know that people are using water. I mean, that's such a good idea to use water as a, a surface area. You can use a huge surface area to put your, solar panel and trap energy, right?
True. I mean, that is a very nice utilization of the land, because we are probably not limited by the cost of the solar cell itself, but the land. There is
Space. Yep.
there is no land to live. Where would you put your solar panels?
Yep.
That's the point. So in Singapore and maybe places like Dubai, they are very, very uh, serious about it, and they are installing solar panels everywhere, even in the water. Very beautiful. India, in fact, is doing phenomenal job over the past 5 years. They have doubled up their capacity, and they are still committed to do so. So they are on a very good track. If you go to Switzerland, you'll find this beautiful building, transparent solar cells, semi-transparent solar cells. So good for aesthetics as well. At the same time, it converts the energy. And you have a plane that's called Impulse. So this plane is completely powered by energy provided by the sun. So these innovations are happening. And one very nice example, that even the first episode of this channel, if you go through, it was on satellites, and how satellites are powered basically because with the solar cells. They have solar cells on their wings, and they rotate, basically they track where the sun is, because in the space you don't know, the sun moves. So as the satellite. So the solar cells has to keep track of where the sun is moving, and then they maximize their energy output.
And that's the easiest way for a satellite to get energy also, because they're close, they're up in air, and that's the only way to get a lot of energy for them. So yeah, that's the best utilization of.
Yeah, satellite cannot park on a
Yeah,
diesel station and pump itself up. No.
true, true.
And these solar panels, which are installed on the satellite, fortunately or unfortunately, fortunately because they are very, very efficient, unfortunately, they are very, very expensive. You cannot use these solar panels for your purpose. Good for satellites, because there the value doesn't matter. I mean, you are okay investing more, but then you need good output. For us, we need affordable solutions. We already have grid electricity coming up. If you come and sell me these solar cells, then I'll say my electricity is cheaper than your solar cell. Why should I buy? I don't care about the planet.
True.
Okay, so far I have talked about solar cells. How do they look like? Pretty much, that's information maybe you
Yep.
already know. Let's
Yep.
go into
Yeah. So if you want to talk more about the scientific background behind it, that will be interesting to know.
yeah. So how we do it in the lab,
True.
only from the lab to the market. Okay, to make understand to the audience, and I assume some of them know a lot, some of them maybe are very know only the basics of it, but we all know light. White light comprises of 7 colors, and if you are happen to see this beautiful rainbow, I think you must have seen once in your life, or maybe more than once. You can see the light is composed of different wavelengths. That's how it's depicted in different colors, and they have different energy. So the first demonstration, if you go back, rewind to 1905, Albert Einstein, what he showed is that when you shine light on a surface of a metal, the electron present in the metal can be ejected out. And the reason is that the electrons in the metals that are loosely bound, so they are nicely living in their houses, when the light comes in and tells them, hey, okay, you have now enough energy, they can be knocked out of their
House.
levels. So they are basically emitted. Plenty of applications you see it of this photoelectric effect, and for which Albert Einstein was in fact awarded Nobel Prize. So the whole idea was from this, that the light can do something to the real metals. We knew it that the plants were doing it already, but this was the first demonstration that okay, a matter can do, a light matter interaction was started from this. So how many materials we can use this with? Does all material would show this property? No, because all the materials are made up of atoms, right? We all know the indivisible unit, the atoms. The way the atoms segregate their composition defines the property of the full specimen, and we categorize them on the basis of a material that conducts more, that has more electrons, a material that does not conduct electrons because the electrons in the materials are very tightly bound, and in somewhere they are a bit loosely bound, so the light can actually knock them off. So you have three categories here. You take the atoms, and in the atom, electron lives in a certain energy level. So electron knows the living room where it is allowed to move. When you bring a lot of atoms together, the electron has multiple living rooms to roam around. Now electron is confused because now it is not stick to one atom, rather it is allowed to go to thousands and billions of atoms around. It is freely moving, but it is still bound to the media. The guardian in the house is still there, the nuclei, it is still bound. So, given their atomic configuration and composition, how tight the electron is bound to the nuclei, that force is different. So, in one where the force is highest, you call it insulator. So, even if you shine light, they are not ready to move their house.
True.
In the metals, they are always there, but they are useless for us because we don't want the electrons to fly off the air. We want to control it somehow. And we do
Yeah.
semiconductors, which are in the middle. You have a certain energy band gap. That energy band gap value is provided by the light. So that has enough energy to excite the electrons, which are bound to the nuclei, and go and to become relatively free to move. When they become relatively free to move, you plug the wires and make them move around the circuit. That's what the electricity is, the movement of charges, right?
Very, very well explained. Yes.
So we are interested in semiconductors with the, how do we do it? Okay, let's look at the first picture. Okay, if you look at that animation, the light shines on the material with a certain band gap. Electrons are now excited, which means now they are relatively free to move, but they are still within the crystal, they are still within the material. They are not flowing around, they are not doing anything for you. And electrons does not have the brain, unfortunately. They cannot move around by themselves. You need to have a driving force. You need to create a situation so that the electrons with this living in the media, which is the bottom figure, if the electrons are relatively free on the top, how would I make them flow around the circuit? And the way we do it is uh, okay. The way we do it, if we want to make the electron moves around in the right direction, there is something you know already known as diffusion. Diffusion is something when you have a concentration gradient, somewhere the density is high, somewhere it's low, then the flux would move, right? If you take a bucket of water, you put some color in it, it starts diffusing in because it simply tries to equilibrate the concentration. You create a concentration gradient that's called homojunction. You dope the material, you make somewhere electron density higher, somewhere lower, they will move it. Or you create an electric field by putting up contacts, like you put some metal contact on the left side and on the right side. They create an electric field, the electron goes out of the circuit and takes the full path and then neutralizes these holes. And in this process you have a bulb that I'm showing it. Basically it's the flow of electron, you have electricity. Now it's the flow of electrons, which you call it electricity. But can you use those electrons for something else as well? Yes.
Okay. So yeah. So before we go there, I have a very quick question. So you mentioned that when you dope it, right, with some other material or some other metal, right? So after doping to a metal, that metal becomes semiconductor, or you do doping in
In
semiconductor.
semiconductors, let's take a semiconductor, which we all know silicon.
Huh.
And we physicists or scientists who are working in electronics engineering, electricals, we are not interested in perfection. We don't want perfection.
Yeah. You want other way around.
If the crystals are perfectly aligned, nothing moves, it's an uninteresting system, a system that we are not interested in. If you create a defect, let's say you remove one atom and then you create chaos, then the things become interesting. So you need defects, but those defects should be deliberate defects. You should be able to create or destroy them by your own will. So then you can control the electron generation or not.
And their movement.
So you
Okay.
can make the semiconductor less doped or high doped depending on those defects. Those defects could be intrinsic, meaning you take something out, or it could be you put something from outside. Then it becomes extrinsic doping. That more of becomes terminology of the semiconductor physics, but let's deal with it as of now. That
Okay.
is to demonstrate the principle.
Makes sense.
What you can do with these electrons? I said that electron flow is nothing but the current, the electricity. But if you take these electrons, and let's say if you have to drive those some reactions, let's say you take carbon dioxide, the first reaction, you need two electrons to get this proton, 2H plus, which is hydrogen ion. To make this fuel, if you don't know, these are very valuable fuels like methane, ethane, and even higher order hydrocarbons. These are the fuels that we use it in daily life. If you take CO2 from the atmosphere, take the electrons from what you have generated from your solar cell and drive this reaction. And this reaction has a certain energy. And that energy has to come from the sunlight. So you see what you have done essentially in this process. You have converted the photons, like the sunlight, to the fuels that you need. Very clean process. You don't have. Otherwise, this process is a very dirty process. If you go in the industry, this is. But that's how we are living with it to generate these hydrocarbons. And you have bunch of hydrocarbons that you can create. You need higher energy. You need a lot of research here. You need catalysts to drive these reactions. And that's what the scientists are doing right now in the lab to make these processes more efficient.
Okay.
um, and also if you take the water, you can split the water, like you can break it. You have protons H plus and oxygen. So you take the oxygen out, and that H plus you can make it hydrogen by reducing it and store it somewhere, and that can become your hydrogen fuel, which actually a lot of people are working on it. The hydrogen storage is a problem, but that fuel you can generate by doing this reaction, which happens at a certain energy, and that energy is provided by the sun. Beautiful concept. But what material does it? So far, I am just saying in there, okay, you take a semiconductor, you do this and that. But specifically, what are the semiconductor? One we all know is silicon. Like silicon, we have it in our chips, we have it in our mobile phones, every electronic equipment, silicon, right? So that's a material which is abundant. It's everywhere in the form of silicon dioxide. If you go to the beach, you find sand, which is nothing but silicon oxide. What you have to do is to break silicon from the silicon oxide. That bond you have to break. That is a pretty strong bond, by the way. That takes about 1,000 degrees to do so. Very energy intensive process. So silicon itself is available a lot, but the process of extracting silicon from silicon oxide is not so cheap. Okay. um, it's non-toxic. It absorbs the light because it has a right band gap. It turns out that silicon is not alone. You have gallium arsenide. If you mix gallium with the arsenic, gallium arsenide, you have cadmium, tellurium. And what I am doing right now, my research deals with, you see, what material you choose, you get different solar cells. The top ones you are seeing, this is multi-silicon, multi-crystalline, monocrystalline silicon, like a single crystal of silicon. And that is about 300 micron thick. You know what the 300 micron is? If you pluck your hairs out, make a stack of 5 hairs, that would be equivalent to 300 microns. Your hairs are about 40 to 80 microns. Mine may be a bit thinner. But
Same here.
that's the order of the thickness, but still that is too much, because if you have too thick material and you have to make it less defective, you don't want more defects to be in that thickness. You have to make it really really pure, and that process becomes more energy intensive. So it requires a lot of energy uptake to create such silicon. And during the energy, the energy that you use to create such silicon also requires the fossil fuels, because the energy
Exactly. Yeah, that's the thing. Yeah.
then you don't remain carbon neutral anymore.
Yep.
The process of creating a clean energy generates more CO2 than that. So it nullifies the whole purpose. So for that, and also you cannot cover the whole area with the silicon. You need to come up with some engineering solution where you do the process at low temperatures. So you see, you have thin film solar cells, which are very, very thin, hundreds of nanometers, 500 nanometers. So take your hairs, divided by 100 or something, so thin. Okay, that can be used for the solar energy conversion. That's what I am doing right now. You have some solar cells, something like paints, we call them organic solar cells. So these are the materials which are made up of organic matter. You can simply paint them and put it like a sari, and you can put it anywhere you want, and it will be very easy to for my mom, who was old enough to deal with a sari, and she can simply use organic solar cells to put wherever she wants. Well, sounds like very utopian concept, but that's the whole idea behind it.
So
You have
is there any way students or kids, if they wanna, harvest solar energy, they can do it at home or some sort of experiment or
well,
demonstration kids can do?
when the whole idea was shifted from the silicon to the these paintable solar cells, yes, there have been some workshops. Even I myself have been a part of such workshops where we have created dye sensitized solar cells, what you see 13% here. These percentage are the efficiency of these solar cells. You can create them using dye, the dye which is there in the fruit. When you extract, it's red color or green color, whatever. That actually absorbs the light. That's why it's a very strong pigment that absorbs the light, and you need two contacts to separate the carriers out. So dye
Yeah.
absorbs the light, which is the juice, and then you have a titania, which is even in your toothpaste. You make a paste of your toothpaste. You
Okay.
just make a coating, put
Okay.
this dye, which is extract from the juice, and then the other electrode would be a carbon, because carbon is also a good conductor of electricity. Where would that come from? Take a pencil, your graphite, you rub it on the conducting plate, that is a carbon. Then you sandwich all of them up, an electrolyte in between. That's it. That's all technicalities. Your solar cell is ready. So we have made these solar cells in a matter of 20 minutes by extracting the juice. But
So
those are not efficient. But
yeah,
you can make.
yeah, obviously, but that's good for demonstration. So is it possible that in future we do a one more session about doing this demonstration? I think many students will be interested to see a live demonstration, that even something which is like juice, which is colorful, and using that thing, we can utilize that and make a solar harvesting system. That's pretty interesting to see live. I mean, I have not seen something like that, but I'll be very happy that if we could do one session in future to do these live demonstrations, and will be.
Yes, I mean, there are a few videos present already in the YouTube, but yeah, it will be a very nice exercise, like
Yeah.
how starting from scratch, what we do.
Hmm.
And even the high school students do in the universities, let's say in Uppsala or somewhere in Europe. This is
Okay.
a student exercise.
Okay.
Yeah.
Okay, that's interesting.
So now, with all this, how do we know the efficiencies? Basically, we have a database, and we go to the National Renewable Energy Lab that's in US in Colorado. What they do, you have different solar cell technologies, and they evolve every single year. So next year, the efficiency will be higher. These are certified efficiencies. So there is an agency that certifies, and that they put everything in this chart. So if you are new in this field, and if you want to know what solar cell technologies are there and how much efficiencies they have achieved, the certified, you can refer it to this chart. That's called National Renewable Energy Lab chart. That is just for the audience who are more interested in knowing the actual numbers, how many, the evolution, the learning curves, etc. Now I'm coming specifically to my research, what I do in
Okay, yeah. So that's interesting part for viewer, because now we understood overall that why solar energy harvesting is important, or energy harvesting is important, and how we can go to the green energy, so that there is less CO2 emission, and that's how we can save planet. But that's an important part where we want to know that, okay, we see there is solar, plates and a solar system, and it is being used here and there, but why we don't use it on daily basis? Like, why that's not the ultimate source of energy, number one. And number two, what are the other things which is being done? What are the questions being asked in this field? Like, if someone wanna become a researcher in this field, what are the questions they can work on? What are the questions they can handle? So if you want to talk about that, including your research, will be interesting for us to understand and learn from them.
Okay, so if I may categorize your question in two parts. One is that if the solar cells are there and the problem is that big, why are we not seeing them around us?
Yep.
We all know it's a grave problem. For that question, I must say that everything is pretty much dependent on silicon as of now. If you look at the solar market, it's mostly silicon, 90%. The other stuff, the 10% is thin film cadmium telluride. That has really not picked up. I mean, the manufacturing companies are mostly in China and Germany, and over the past 10 years, China is massively producing those solar cells, which is good for solar, but then it disrupts the whole economics. And government also has to play a part. For example, if a solar cell is that expensive for me that my electricity that I get from the government is cheaper, why would I buy? I mean, I don't buy this argument of global climate change. I mean, that's normal audience, that's how they think.
Yeah, that's
That
true. Yeah, that
so
they're
to
more
make
concerned about their economy. Yeah, that how they're
so
gonna
to
run their
make
house.
to make it cheaper, government gives subsidy, so they encourage you to do so. But now the sometimes because of policies, the subsidies are not widely available. And rather than giving solar cells to distributed customers like individually I have, they are mostly making up a big plant. Like in Tamil Nadu there is a big solar plant, like in Gujarat you have a big solar plant. Those kind of facilities are sprouting up. You buy cells from China, install them up, no big deal, it's fine, good for the photograph as well. But for really the distributed, the to give to the customers, these things have to be conveyed to the public, that what you can, I'll show you in the later slides, not only the benefit of clean energy you can become a businessman, you can earn your own money. You don't see them, yes, because the silicon cells are expensive. That's the answer to your question.
Okay.
And
Yep.
we don't have area. We are not as lucky in our homes as you see in Uttar Pradesh village, where we see land all around us. You go look at Singapore, look at megapolis. People are fighting for land. They don't have place to live. Where would they put their solar cells? So these types of novel concepts are coming up. Thin film solar cell, where you can install them on the windows, don't care about the land, put it on the sea, slowly picking up. So good stories are coming up. Very hopeful about it. Second
True.
question is, what is the research? What are you doing then? Are you reducing the cost? No. My job is to make these thin film solar cells more efficient. They are not as expensive, as efficient as silicon. Why they are not as efficient as silicon? Because they have defects, uncontrollable defects. I said we want defects, but we don't want defects that are not obedient. We need obedient defects, so to say. We want defects to create as per our own will. So for that, we first need to understand what are the different defects that are there. And in this slide, I'll mention you whatever to answer your question. It's all there in this slide. Okay, it all started with a very fancy idea of using natural single crystal. You see it in the mountains, those beautiful crystals. So they are actually good solar energy converters. They are semiconductors. You can use them. That's pretty good. That are naturally available energy sources. So my PhD started from using a natural single crystal, which is chalcopyrite. In geologists, maybe they would know this better. They have a certain crystal structure. We call it chalcopyrite crystal structure. It has four elements: four: copper, indium, gallium, and sulfide. They form a specific crystal structure. If you remove one atom from their place, the whole performance screws up. And that one atom, where it goes around, how much atom you can remove, how much you can put, is a question mark. And how
Mhm.
bad it affects the performance, that is a question mark. That is what we are trying to understand. So what we do, we make these materials very thin. So what you see is, this is a cross section of the film. What you are looking at the film from the side is the thickness, and you see the thickness is only 2 microns. Your hair is 80 microns, 40 microns, I said. You see, 10 times less, 20 times less. And then we see what it looks like. Where are the defects to prove that? And how do we see the structure? Let's say when we make a material, we try to see what is the crystal structure. We use x-rays, the same x-rays that you use when you go for the medical examination, okay, to see the bones, etc. We use the x-ray illumination to see the crystal structure, because x-rays can really penetrate more and they can tell more information of the interior structure. An electron beam, you shine electron beam and see how electron beam interacts with your material. And that's the way we characterize it, how good or bad it is. We use lasers. We shoot very high energy lasers on the material to see what damage that the defects, the crystallographic defects, does to the performance. So we use very high energy lasers, very cool lasers. And then we check the performance. And this is a loop. You see, this is a feedback loop. We do it, we vary something, and then we check, we vary something, then we check, then we check the performance. When we know, when we establish something, we publish it in an international journal, so that the community, they all read it, And if it is convincing enough and it's very impactful, maybe we hope one day it will make it to the market. And that transition from the lab to the commercial market is a big gap. To bridge it, you need startup, you need innovations, you have those incubation cells that you have in the university. It's a lengthy process. So you have to design it in way. That's the vision, that you take a material, make it, try to understand defects. Maybe you hypothesize some theory, or maybe your goal is to make cells which are very efficient. It depends on your goal. Okay, that's how the flow of research it goes roughly.
Yeah.
But that's the future I envision. So with this, I'm kind of wrapping up everything. So this is the future that I envision, is that you have a solar cells on top of your house, which is connected to the grid, the energy company grid. They give you the energy when you need energy, and when you are generating enough energy from your solar cells, you can actually fed the energy back to the grid, and
Hmm.
in government or the electrical company will pay it for you. So you see, you become a businessman. You are the manufacturer of energy because you have created energy on site, and that energy you can sell it to the grid, and then you can make money out of it. And when you have excess energy, you can do the fuel generation. You can not only use the electrons for electricity, you can use those electrons to drive nice reactions and to have stored these valuable fuels on your basement. So you see, at your basement you have fuels which you can use it to power your car, or maybe you have the clean energy source you can use for electricity, and when it is excess, you sell it to the grid and make money. I mean,
Makes
all three.
sense.
But
That's
it's
a good idea.
fetched. It's an idea which is a little bit far fetched right now, at least, but it's practical. It's not something which cannot be achieved. The main hurdle is that the sun has a very nasty problem. Do you know that? The problem is that the sun does not shine 24 hours. It goes in and out every single day. So in the evening, when you do not have sun, you are not that businessman anymore. So you need storage. The battery research has to cope up with the energy generation. And if that lacks, you cannot store the energy, it's useless. I mean, it's useful in the day, but in the night, you have to have batteries. Another problem is the duck curve. Or what you look at your screens right now is a duck, right? It resembles pretty much like a duck. We call it duck
Yes.
curve. So
Hmm.
y-axis is the demand, the energy demands which fluctuates. In the night it goes down, and in the noon, sorry, in the night it remains pretty much stable, and in the noon the demands dips because everybody's um, in the offices. They are not using their air
Electric.
conditioning,
Yeah.
and when they come back from their office 5 6 p.m., the demands picks up. So you see, if you have more solar deployment, you have more energy from the solar cells, you have more generation in the afternoon when you need the energy least. That is not the time when you
That's
need
true.
the energy
That's
more.
true. Yeah. Yeah, that's true.
So what happens in the daytime, your demands dips, so that the energy that you demand from the grid falls down rapidly because you are already having a lot of energy. In fact, it dips so much that the cost of the energy becomes negative. What that means, the company tells you to switch off your solar cell, I'll pay money to you. So basically, they
Hmm.
will give you the money in the afternoon for doing nothing. And in the afternoon, when the demands picks up, it becomes very difficult for the grids to cope up because it's a very intensive process for the grids to maintain at a certain energy. If you fluctuate them, there is a danger of grid failures, etc. So if
So,
they
so what if they have mechanism to store, like you are talking about these battery, where there are a lot of good research going on to improve the efficiency of battery. So they have the mechanism to store the surplus energy, and so that they don't ask us to switch off the solar system. I mean, any surplus energy they have in the daytime, they can just store it and use it in the night time.
that's precisely the point. To defeat this duck or let that duck not come into our way, innovations, we need innovations, and we should not only think in terms of solar versus fuel, this versus that, or nuclear energy is bullshit. No, the thing is, it has to be complemented. At the end of the day, we should not be the enemy of fossil fuel or any technology whatsoever. We have to think how can we incorporate it to the best solution out of it. It's not a good idea to discard something and just say that we are not going to become fossil fuel free next day. It will take a process. So my takeaway from this is that we can defeat this if you have the good proper energy storage, you have the grids that would be capable enough to cope up with this fluctuation.
Fluctuations, yes.
And yes, and you maybe you need something else also here which I'm missing and would be too long. This discussion would be too long. Second thing is that I am mentioning it by myself is that you are mentioned about, I mean, we all are hearing the term electric cars. Very nice, cool, beautiful. They are clean energy sources. But think about it this way. Electric cars are cool, they are clean, but you have to recharge it, and the energy that you are using to recharge it, where it's coming from. If that's also coming from the fossil fuels,
Fossil fuel, yes.
it's kind of a good that you are reducing the emission from the transportation, but at the end of the day you need that energy that you are using to recharge the vehicle should also come from the solar, then only the whole process would become carbon neutral. Otherwise low,
Carbon free, yes.
but in the big picture it doesn't solve the whole game, the
Yeah.
big game.
Maybe I think the idea is why people is more excited about these electric vehicle is at least you don't see that pollution on road, because if you drive a car with a petroleum or gas, you emit a lot of exhausted gas there while you're driving. At least you don't see those things while you're driving on the road, but it's not carbon free solution. That's what you're trying to say,
Yes.
right?
And we have this obsession. Of course, it's a balance. Our growth is measured in terms of how many cars we buy every year, isn't it? If
Yep.
the automobile consumption goes down, we say economy is running into recession. But it's a little bit of an obsession. You need to think about it. What do you want? An economic growth, or you have to balance and you have to convince yourself that if I can use a bicycle, which is good enough for my purpose, maybe I should stick to it. We should encourage
Okay.
such
Yeah,
practices.
that's true. Yeah, that is what happens in most of the European countries. Like, they prefer to have, a bicycle. Yep.
So with this, I mean, this is the final slide. I will not eat your heads anymore. It's already quite long.
No, it's
Uh,
it's it's going wonderful. Yep.
the takeaway is that it is our last chance, probably the last, to do something for the cleaner climate because we have already slipped up. The Paris Agreement, which says that you have to limit global climate temperature rise to 1.5 degrees, we have already missed that goal, which we have done it in 2016, the Paris Agreement. We are going to miss it horribly. If you remove this corona crisis, the way we are going to hit 2 degrees very soon, in maybe 15 or 20 years. That is not good.
Yeah,
And
so that's a valid point, because see, with you are putting in a right way that if you compare with this pandemic, right, you saw people dying, you saw people getting affected, and then there was a very aggressive research to handle it, because we knew that if you're gonna get infected, you cannot go outside, you cannot do socializing, you cannot meet people. So everyone was like, what scientists are doing, why not there is a vaccine, and everyone was looking up to, like, where is the vaccine. But we don't see the effect of these global warming directly from our eyes. So we are not very panicking. We are not in a panicking mode, but we should be. That's what I think you are trying to say, that we have to be in panic mode, and we have to take these global warming very, very seriously, and we have to do whatever we can to save our planet.
yes, and I hope I have convinced you and to everyone else that the global warming that we are saying is not based on our experience. It's not that 10 years ago I used to feel more cooler than what I'm feeling now. No, it does not. It has nothing to do with the feeling of my grandmother and mother and myself. It's based on the data. We have looked at the data that CO2 is going up, temperature is going up, that sea levels are rising. So if someone tells me that 10 years ago, we used to have very cooler climates, no, 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 that's a feeling fine. But to quantify something in science, you need data. You need epidemiological investigations to see it. And I hope I have conveyed to you. And the last
Yeah,
thing, yep,
yeah. Go ahead.
and we do not inherit the earth from our ancestors. No, we are borrowing it from our children. If you are okay, no issues, it's fine. So for the whole broad, for your channel, what you saw in these slides, that it does not take only a guy like me who is working in semiconductor physics to do it alone. You see, you need climatologists. So those who are interested in climate studies are a part of this. You have physicists, chemists to know what's going on in the material, electrical engineers because you saw the grid connection. Economists have to come up because ultimately it's the policymakers that have to decide. No matter what we discuss in the table, but it all rests on the shoulder of the leaders that we elect. And if the policies are not right, it will end up nowhere. And data scientists have to play the role. And you see, this is the problem where almost everyone comes into the picture, not just a scientist like me working in semiconductors.
Okay, so now if you want to go, you can go to the, you can remove the PPT and you can come to the stream mode. Okay, so that was really wonderful talk, and it was very. I mean, we got enlightened with the fact, knowing that how solar system works, why it's important, how we can save planet. So thank you for having very good, a nice presentation. It was very well presented. But before we let you go, we have a couple of questions. I don't know how many we can take. There are many questions, but we'll try to take at least one or two because we are already, it's 1 hour show. So we'll try to take one or two questions and then I'll let you go. Let me see if what question we can take. So there is one question. You can see that question on your screen also if you want. Uh, so it says, Sweta Sinha, she is saying that a very interesting talk. Thank you, Dr. Sukla. And my question is what we can do on day-to-day basis to help the planet.
Well, really excellent. I really like this point because we need to know our role, what we can do.
Yeah.
What we can do is that first of all, we have to convince people around us that it's real. This is really nonsensical that even after so much of we have convincing data sets and we are still trying to be ignorant. We don't acknowledge it is that's a problem. We first have to acknowledge it. Okay, number one, you have to acknowledge it. Second one, if you are seeing the wastage of the energy, because we are still dependent on fossil fuels, so we have to reduce some little bit minimalistic. That's maybe not good for economy. We have to be considerate. I'm not saying don't do essentialities. You have to do it. Be considerate, and also you have to promote renewable energy sources. Maybe if you are eating your food, you are wasting. Let's say in our here in Europe, the culture is that if you are going to take the food, you have to have your own utensil. The green you do not waste it around. Like you go and take a new one and throw it. So these habits are actually picking up more and more. We are seeing people carrying spoons in their pocket,
Oh,
right?
that's very interesting concept.
In India, it sounds crazy to have carrying spoons and knives, all those in your pocket. But this is slowly these habits are coming up,
No,
and all.
that's a very valid point because for a long period of time we have been using these fossil fuel for a long period of time, and we're very ignorant about it because it just comes. You pay money and you get energy, but we don't know that it's not just what money you are paying for it. There is a bigger cost behind it, and if we don't, as you said, that on day-to-day basis, if we don't start, saving energy to our capacity, it's very that's where we can contribute to save planet by using as less as electricity we can use, or any sort of CO2 production we are contributing, and we can try to minimize that.
And for Shweta, I think one more thing I would add to your question, that if you have to look at the examples of you need to know the success stories, and the success stories are, let's say, California, which uses 11% of its energy from renewables. You have Germany, you
Yeah.
have Scandinavian countries. You need to see what they have been doing successfully, what we are failing to do. Maybe that would provide good clues, the lifestyle, the way we approach to this problem. Yeah.
Okay, so we'll take one more question probably, and then what we can do is there are many questions, so we'll try to answer those questions in the comment section. For the viewers who is watching it for the first time, after the live session is done, we'll post this video on our YouTube channel, so you can anytime go back if you missed it, in the beginning or any part of it, or if you're joining it later, you can always watch it on our channel, and then we'll try to answer those questions in when it will be uploaded on YouTube channel. So you can always go back and find the answers for the questions you asked. We'll try to take one more question and then probably. So this is someone NKB whatever. So he or she is asking what's the difference in efficiency between satellite solar cells and regular solar cells.
Fantastic. I was expecting this. So the regular, so first of all, there is a limit to the performance. Like there is a practical limit to it. Like we cannot even go beyond theoretical limit. If you make a single junction solar cell, okay, these are more terminology of solar cells. We cannot go beyond 32%.
For
Okay,
this, okay, yeah.
for the single junction solar cells. even the best we could do. That's the theoretical limit. So the ones that we use are actually 25%, because practically we are only 25, but theoretically we can go up to 32. But the cells that you see in the satellites, they are in fact 45% efficient. If you look at the Enrel graph that I showed in one of my slides, the highest one was in fact 40% or 50%. Now it's even the record is around 50%. They are multi-junction solar cells. Those are solar cells where you have one layer that absorbs a particular spectrum of light, then you put another that absorbs the particular spectrum of light, and this way it uses the full solar spectrum efficiently. Ours, there are a lot of losses. And also, when they make this multi-junction, the technology to make this atomic layers nicely, it's very expensive. They do it by epitaxial process. If we do the same thing for our cells, maybe they'll be efficient, but the price would be skyrocket. But the question he's asking, that efficiency, okay, the efficiency for the satellite ones are close to 50%, 40% plus. Ours is just 25% or maybe 20%.
Okay, so I'll ask two questions. One is a very basic question, very layman question for you. So when we have these solar plates, right?
Mhm.
Say for example, we purchased one solar plate to just have one or two bulb in our house, right? How long these solar plate will work? Like, what is the
You
life?
you mean the solar panel that
Yeah,
you
if
buy?
yeah, that's what I mean. I purchased a solar panel, and
Mhm.
I just want to have one or two bulb in my, which is getting lighted up using the solar panel. How long? What is the shelf life of the solar panel?
Okay, I'll be a little
Is
bit.
it will it work for forever, or it's after a few years it will stop
For,
working?
for silicon solar cells, which are there in the market, they give you about 25% of 25 years of lifetime. That's
Okay.
a balance of system. Like it will work all the way up to 25 years, but every year the efficiency of performance might go down. And maybe after 25 years, it will not be dead, but it won't be sufficient to power the energy needs. But the rule of thumb is that if you want to install a solar panel in your house, first look at the energy consumption. Look at your electricity bill, right?
Mm.
And you can do it very simple exercise. Look at the glass bulb or whatever you are using. There is a rating written at the back. Look at the watt, the number of hours that you use, watt
Mm.
hour, that's the energy
Yep.
specific. We talk about it. Kilowatt hour becomes 1 unit, 2 unit, 2 kilowatt hour. And
Mm.
then calculate it nicely that over a month, how much do you use? And then look at the area that you have. Then you can actually, there are some softwares as well. But to answer your questions, 25 years.
So then that's the second question to me. So once the solar, panel is expired or it become less efficient, do you
Mhm.
throw it, or there is a mechanism to reuse it by doing something like refurbish something? Can we? There is some technological advancement happening in that field to make it, reusable with less expense than making a new panel.
Well, you cannot refurbish it in the sense that you do conditioning and use it. No, after 25 years, you can recycle it because
Okay,
the element is still silicon. You can melt it at high temperature, then it will become again silicon. Then the whole process starts from the beginning.
from the
Like
scratch.
throw single crystal, chop it
Yep.
off, it has solar cells.
Okay, okay, that was a wonderful, conversation with you, and for me also from biological science, background. I mean, I understood each and everything you mentioned in the slide. So I'm very sure that even the general audience, if we have or students from school or college, they must have learned a lot from this talk. And with that note, I want to thank you, and I wish you all the best for your, future research. And we want to see in future that the price of solar panel is going down, it becoming more accessible, more usable, and we switch from all other source of energy like fuel energy to solar energy to save our planet, and we make our world a better world. Yeah.
Yeah, I hope so. That's a dream.
Yeah. So thank you so much for coming and joining us. Uh, so okay, so with that, for our viewers who is watching this show for the first time, I request you all to subscribe to our channel because we do this show every Saturday, and we try to bring researchers from all different field. Next weekend we are going to talk about brain and neuronal connections. So there is a scientist from Harvard Medical School in US, and he's going to talk about some important aspect related to our neuronal biology. So please subscribe to our channel and spread this message to as many as student you can, because as a scientist, what we can do is we can bring researcher from across the globe, but we don't have access to a student. It's your responsibility to spread the message, bring more and more student to this board, and have a practice, have a have a habit to watch this show every Saturday, so that you will get a overall idea of what's happening around in terms of research, what are the different research field, what people are doing in different research field. So you will be updated, and if it inspires you, you can become a scientist. What I'll do is I'll leave the email address of the today's speaker in the comment section, so that if you have any question from the speaker, you can always ask them now or in future also. If you want to become a researcher in this field, you can always contact our speaker and get information from them. That's all for tonight. Thank you so much for joining us. Have a good day and take care. Bye bye. Thank you.